atomic number that tells you about the number of protons became very important to a guy named Dmitri Mendeleev. He was a teacher out in Russia and a scientist, a chemist, and he was teaching organic chemistry, and he was trying to figure out a way to help his students understand the known elements at the time. Notice that he lives in 1834 to 1907, so they didn't have the full 118, but they still had quite a few. And they were awfully hard to memorize. They didn't know that there was any system. And so Mendeleev was looking for one. And what he did was he lined up all of the elements by their atomic number. So hydrogen was 1, so it went first. Helium was 2, and so that was next on the list, and all the way down. And he had the first 20 at that point in time, and he started looking around. And what he noticed was he started comparing the properties of the elements. He said, helium and neon act pretty much alike. And lithium and sodium are also very similar. And hey, what about that? Beryllium and magnesium. And if you notice, every 8 atoms, or every 8, right? 2 to 10, 3 to 11, 4 to 12, we see a repeating property. And so Mendeleev thought he was onto something, and he starts arranging things. And he starts making groups. He says, if they act similarly, I'm going to stack them on top of one another, and I'm going to keep preserving my arrangement. And so number 1, hydrogen, and 2, and 3, and 4, and 5, 6, 7, 8, 9, 10, etc. He just kept going up. And sometimes he found some gaps. So down here, when he got to potassium, right, potassium is 19, and calcium is 20. And then there were a few elements out here in his list. And there were some spaces in the middle. All he did was left those as gaps. He said, there's something there, and it has not yet been developed, and it has not yet been discovered. And so he saw these clear divisions on the periodic table. He saw columns where things were very similar to each other. He also saw that if I leave gaps, I expect these things to show up. And sure enough, these 3 elements, scandium and gallium and germanium, that he left as gaps were discovered within the next several years, proving him right and saying that there was something to this system of his. And so from that, we get the modern periodic table. And there's a few divisions that I want to take a look at today. So if we look at the periodic table, by and large, most of the elements on the periodic table, right, everything that is highlighted in green, is classified as what we call a metal. Most of what's left, in blue here, are nonmetals. Notice that we've got some oddball here, hydrogen, right? It's in the middle of metals. This is, go ahead and erase that so that I can really put the right chemical symbol in there. Hey. And so we can put hydrogen there, right? Hydrogen is the oddball. It looks like it belongs with the metals because of where it is placement-wise, but it really doesn't. One more grouping that we've got is the metalloids, and the metalloids just straddle the line between metals and nonmetals. They're not quite one and they're not quite the other. Property-wise, we can see some similarities. Metals are mainly solids at room temperature. Think about all the metals you've ever seen. They're shiny. Metals are very, very often shiny. They're malleable. It's easy to pound them out and make sheets out of them. They're ductile. Ductile just means it's easy to draw them out into wires. So malleable and ductile are both different ways of saying that metals are pretty soft. Lastly, metals are conductors of electricity. Think about your wiring in your house. We use copper wiring. We don't use wire made of nitrogen. There are other reasons that we wouldn't, but that's one of them. Metals are used in a lot of things, right? It's easy to make wires and foils and sheets out of metals, and they're very conductive, so we do a lot of that, and so we make a lot of those sorts of things. We make coins and jewelry out of metals. We make building materials out of metals. Nonmetals, on the other hand, are dull. Metals were shiny, nonmetals are dull. Metals were soft and malleable. Nonmetals tend to be pretty brittle. Sulfur, for example, you can see all of the crystalline structure on that. If you hit that, that's going to shatter. Whereas a metal, when you hit it, it's just going to pound and get out of the way. Metals were solids. Nonmetals can be solids, liquids, or gases. Sulfur is a metal, or a nonmetal, sorry, that is solid at room temperature. Chlorine is a nonmetal that's a gas at room temperature. And right here is bromine, and that's a liquid at room temperature. Lastly, nonmetals are insulators. That means that they're poor conductors of electricity. We'd make a wire out of copper, but not out of sulfur. Nonmetals are found in a lot of different things. One particular use for nonmetals, the so-called noble gases, neon and argon and krypton and xenon, is in neon lights. They're very useful for that. Nonmetals are the biological building blocks. You are made primarily of the elements nitrogen, oxygen, carbon, hydrogen, phosphorus, and sulfur. There are a few other elements that you're made up of, but those are the predominant ones. These are what are found in proteins and in DNA. Nonmetals are used for medical uses. That oxygen that we like to have you breathe in the air is very good for medical uses if you're having problems breathing and if you're having problems getting oxygen to the places you need for brain functions and for muscle functions. Nonmetals are dyes and bleaches as well. So the same things, same nonmetals that you can use to stain your clothes are the same ones that you can use to clean them if you change up the chemical compound just a little bit. Our last class of compounds is metalloids, and metalloids are mixed metallic and nonmetallic properties. They're not quite metals, but they're not quite nonmetals either. They're semiconductors. So metals were very good conductors of electricity, nonmetals were very bad conductors of electricity, semiconductors are somewhere in the middle. Lastly, it's not really a property, but these are along the stair-step line of the periodic table. So if I draw my little periodic table here, there's always in bold this stair-step line, and nonmetals are to the right of the stair-step line, metals are to the left, and metalloids touch. So it's just a very, very small region of the periodic table. Silicon and arsenic and antimony and germanium are some of our main metalloids here. Lastly, we find them in a lot of things. If you are using a cell phone right now, or you're using a computer certainly to watch this lecture, you are using silicon and arsenic and germanium and antimony. The semiconducting properties of metalloids make them absolutely optimum for chips, for computer chips, which are found in pretty much everything we use. They're found in solar cells. Solar cells are mainly made of a silicon coating. Again, that has to do with the semiconducting abilities of them. Another thing that you find a lot of metalloids in is glass. Glass is silicon dioxide, and it's just melted down and it's shaped and it's fused in a way that we want it to be made.